Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about hypothesis testing, which is a very important statistical technique that is used in essentially every scientific domain to determine whether the observed data support a certain hypothesis or they can just be explained as being caused by random noisy fluctuations. The reason why I'm holding this toy die in my hand is because we're going to apply the hypothesis testing framework to study a very important question, which is whether this toy die that I borrowed from my daughter is fair or not. Let's take a look. We're going to introduce important concepts in hypothesis testing, which include the null hypothesis, the test statistic, and the p-value. The ultimate goal of hypothesis testing is to check whether the data that we observe support a certain conjecture of interest. We do this by playing devil's advocate. We say, maybe the patterns in the data that seem to support this conjecture are just caused by random chance. If this is unlikely, it is extremely unlikely for random chance to have generated these patterns, then this is interpreted as evidence in support of the conjecture. Let's take a look at the data obtained with this die. So here, the numbers correspond to colors. So in particular, purple is number 3. And what we observe is that there are a lot of 3s. This is just the empirical PMF where we have normalized the counts. We see that the empirical probability of a 3 is much higher than 1 divided by 6. So here, a natural conjecture is that the probability of a 3 is larger than 1 over 6. So now we have to take this devil's advocate perspective and try to see whether the data can just be explained as random fluctuations in the under the assumption that the conjecture does not hold. This assumption that the conjecture does not hold is called the null hypothesis. The null hypothesis is that nothing interesting is happening, basically. Our conjecture of interest is not true. In our case, our conjecture of interest is that the probability of rolling a 3 is greater than 1 over 6. Or 1/6. So a natural null hypothesis is that that probability is actually equal to 1 over 6, or alternatively that is smaller or equal to 1 over 6. It won't matter very much, as we will see later on. In this context, our original conjecture, in our case that the probability of rolling a 3 is greater than 1 over 6, is called the alternative hypothesis, because it is alternative to this null hypothesis, which captures that nothing interesting is going on. In order to evaluate the null hypothesis, we need to look at the data. In order to do that, we design a test statistic, which is a function of the data that is associated to our hypothesis of interest. This test statistic should be large if the null hypothesis does not hold. Okay? We actually design this test statistic, so we need to make sure that it captures the structure in the data that is important for our hypothesis of interest. In our case, we are interested in the probability that we observe, in the probability of rolling a 3. So a natural test statistic to choose is the number of 3s. Notice that it satisfies this. A large value of a large number of 3s is evidence against the null hypothesis. Our test statistic is large if the null hypothesis does not hold. If the null hypothesis does not hold, that means that the probability of rolling a 3 is high. And it's low, and the test statistic is small if the null hypothesis holds, because in that case, the probability of rolling a 3 is just 1 over 6. So let's take a look at our data. When we look at our data, we see that we rolled this purple side, which represents 3s, 18 times out of 60. So now we can make some assumptions such as that the rolls are independent. And what we would see is that it is extremely unlikely to roll 18 out of 60 3s if the probability is 1/6 or less. It is extremely unlikely. Okay, so is this the end of the story? Can we just conclude that the die is not fair and that's it? I want you to think about this question, so feel free to pause the video and think about it. Because the answer is no. Okay, we have committed a cardinal sin in the hypothesis testing framework, and I would like you to think about what that cardinal sin might be. Okay, why is this really not convincing, what we have just done? So the reason this is not convincing is because we have selected the hypothesis after looking at the data. In order to illustrate why this kind of invalidates our whole procedure, let's think of the following example. Imagine that you're walking down the street in New York City and your friend says like, look, that car has license plate number EMC 6055. 1 million cars drive through Manhattan every day. Isn't it amazing that we saw this particular license plate? It's a 1 in a million chance. So what your reaction hopefully would be to worry about the mental health of your friend, because the probability that you should be looking at is not a 1 in a million, right? Because you have actually seen the license plate number first. So if you had seen another license plate number, you would still say the same thing. So the event of interest is not seeing that specific number, but rather seeing any number, and the probability of that is equal to 1. So this is completely meaningless. In this particular case, this is actually the license plate of a car I used to share with my friend Danny, who helped us out in this financial crisis video in California. So it would be pretty amazing if we saw this in Manhattan. So this is just to illustrate, if we have fixed the number beforehand, then it is amazing. But if we fix the number after the fact, it's no longer amazing. In our case, we're evaluating the probability of seeing a lot of 3s. But if we had seen a lot of, let's say, 6s, we would be evaluating that probability. So we should be really looking at the union of the events, seeing a lot of 3s, seeing a lot of 6s. We could maybe have come across another pattern, which is like very few 1s. So then we should include also the union with very few 1s, very few 2s. Maybe we could have come across a pattern where we would have a lot of, like the even numbers had systematically higher probabilities than the odd numbers. So then we should include that probability also, and so forth. Unless we have fixed the hypothesis beforehand, we don't really know what probability to look at in order to determine whether the data actually are consistent with the null hypothesis or not. I hope that makes sense. So it's very, very, very important, I cannot say that enough, in hypothesis testing to decide the null hypothesis without looking at the data. And then choose your test statistic, again without looking at the data. And then evaluate the test statistic on the data, determine how likely it is under the null hypothesis, and reach your conclusion. This requires modeling the distribution of the test statistic under the null hypothesis. So let's take a look at how we can do this under the framework of parametric testing. In one of the following videos, we will take a look at how to do this in a non-parametric way. In parametric testing, we make the assumption that the test statistic has a distribution that depends on a small number of parameters, which we're going to call theta here. Theta you can think of just as a vector of parameters. If the null hypothesis is simple under this parametric testing framework, then the parameters are going to be equal to a single value. We're going to see an example in a moment. If the null hypothesis is composite, then we're saying that the parameters belong to a certain set. Okay? Basically, this parametric testing framework allows us to describe the null hypothesis in terms of the parameter that determines the distribution of the test statistic. All of this, I think, might sound a little bit abstract, but let's make it very precise with our example. We're going to assume that our rolls are independent, okay? We're interested in the probability of rolling a 3. So a natural parameter to use to characterize this distribution is saying, well, the probability of rolling a 3 is theta. And we're going to assume that it's the same probability every time we roll the die. So now remember that our test statistic is the number of 3s, okay? We're going to use 100 new rolls because we need new data, because we have chosen our hypothesis based on the 60 old rolls, so that those data have to go to the trash, right? We cannot use them within the hypothesis testing framework because we have used them to choose our null hypothesis. Okay, so now we have this test statistic, and we're going to come up with a distribution that depends on this parameter theta. Well, if we think that the probability of rolling a 3 every time we roll has probability theta and the rolls are independent, and we're rolling the die 100 times, the number of 3s is binomial with parameters n equals 100 and theta. And now we get to the point where we can encode our null hypothesis within this parametric framework, because our null hypothesis was that the probability of rolling a 3 was equal to 1/6. And this is this simple null hypothesis where we're saying the null hypothesis is that the parameter is equal to a specific value. In this case, 1/6. Remember that an alternative, I shouldn't say an alternative null hypothesis, because then this is going to get extremely confusing. Another null hypothesis that we could have chosen is a composite null hypothesis where we're saying that the parameter belongs to a set of possible parameters that is between 0 and 1/6. So hopefully this makes clear the distinction within parametric testing of a simple null hypothesis against a composite null hypothesis. Now the observed statistic is equal to 21. Out of the 100 new rolls, 21 of them were purple. Okay. Now, how do we determine whether this is consistent with the null hypothesis or not? The way we do it is by answering this question. How likely is it to observe 21 or more 3s under the null hypothesis? The reason why we say or more is that if the test statistic was even more extreme, then we would still consider it evidence against the null hypothesis. So we're saying, we observed 21 3s. What is the probability that we see 21 3s or more when we roll a die if the die is fair and the probability of rolling a 3 is 1/6, okay, if the null hypothesis holds. Because if that probability is relatively high, then nothing interesting is going on. But if that probability is very, very, very low, then we interpret that as evidence against the die being fair. Hopefully that makes sense. Okay, so this quantity, this probability of observing a larger or equal test statistic under the null hypothesis is called the p-value. We're going to start talking about a simple null hypothesis because this makes things easier. Under a null hypothesis, the p-value is just the probability that the test statistic, when the parameter is equal to the parameter associated to the null hypothesis, is greater than t. Okay? Actually, I went a little bit too fast there. We begin by defining the p-value function, which is the p-value associated to every possible value of the observed test statistic. Okay? And then if we want the p-value corresponding to the data, then basically we just plug in the observed test statistic there. So for our die roll, basically this tells us the probability of observing a number of 3s that is greater or equal to t for different values of t. Okay? So let's compute it for our die rolls. Every time, so we're going to compute the p-value for values from 0 to 100 because those are the possible number of times that we roll a 3. Okay, remember that our test statistic of interest is the number of 3s. And now the p-value function is the probability of observing a number of 3s that is greater or equal to each of those values of t. Well, we've said that this is binomial. Under the null hypothesis, we fix the parameter to be 1/6. Okay, so this is a binomial where we have basically plugged in theta here and then 1 minus theta n minus I. Okay, hopefully that makes sense. And this gives us the p-value function. So in particular, now we can plug in the observed value for the test statistic here, which is 21, to obtain the p-value for our observed data. And that p-value, the probability of observing 21 3s or more under the null hypothesis, that basically the probability of observing a 3 is just 1/6, that probability is 0.15, 15%. We'll come back to whether that is large or small in a moment, but first I want you to visualize what we're doing. So this is the distribution of the number of threes that we observe under the null hypothesis that every time we roll, the probability of rolling a 3 is 1/6. It's binomial. And what we do is we say, okay, we observe this number of threes, which is 21. So what's the probability of observing 21 or more? We just sum this PMF from 21 to 100. Of course, at some point it becomes very small, so that's why I'm not even drawing it. Okay, so that gives me a p-value of 0.15. If we had observed another value of the test statistic, we would have obtained another p-value. So here you see that the p-values for a small number of rows would be very, very high, because the probability of observing those number of rows or more would be very high. And if we had observed more threes, like 33s or 43s, then the p-value becomes minuscule. The probability of observing that, if the die is fair, is extremely, extremely small. And we happen to be kind of in between, right? Because the probability of observing 21 threes or more is 0.15, which is small, but not ridiculously small. What if we had had a composite null hypothesis instead of the simple hypothesis? In that case, we define the p-value as the supremum over all the possible values of theta. In our case, the possible values of theta are a discrete case, so this would be a discrete set. So it would be just the maximum of all of these probabilities. What we're saying is, what is out of all the thetas that we're considering, these are thetas between 0 and 1/6. I don't have it here, but like in our example, it's between 0 and 1/6. What is the theta that gives me a higher probability of observing this number of threes or more? And then when we want to actually get the p-value, so that's the p-value function for every possible value of the test statistic. If we want the p-value of the data, then we just plug in the observed test statistic, which in our case is 21. So here we're going to see that this is not going to make a difference whether we use a composite null hypothesis or not, because when we look at the supremum of, oh, I said something silly a moment ago. I said that it's not discrete, right? Like, I don't know what I was thinking. I said that this is a maximum because this set is discrete. It's not discrete at all, right? It's continuous between 0 and 1/6. So sorry for that. It's really not discrete. But the maximum is attained. That was what was in my mind. Yeah, I don't know. It's Friday afternoon. These things happen to me. So this is not a discrete set, okay? It's a continuous set, obviously. But the maximum is attained. When is the maximum attained? When with theta is as large as possible, because this is the probability of observing t or more rolls. The higher theta, the more likely that probability is. Okay, so here the maximum is actually attained for 1/6. So we obtain exactly the same p-value function for the composite null hypothesis as for the simple null hypothesis. Why? Because if we're looking at this test statistic where we're looking at the number of threes and we're interested in that number of threes or more, the way to maximize that probability is by setting theta as large as possible, in this case 1/6. So that's why here it doesn't make a difference. In other cases, it might make a big difference whether you're considering the composite null hypothesis or the simple one. So we obtain the same p-value for the composite null hypothesis. So how should we interpret this p-value? A tempting interpretation is to say, well, this means that the probability that this die is fair is 0.15, okay? But the problem is that the way we have modeled this whole situation is from a frequentist point of view. So there's nothing random in this statement. Theta is actually deterministic. So this makes absolutely no sense. It's a little bit similar to the problems with interpreting confidence intervals that we had mentioned in a previous video. What is the correct interpretation of the p-value being 0.15? The correct interpretation is the following. If the die is actually fair in the sense that the probability of seeing purple is 1/6, then the probability of observing 21 purples out of 100 is 0.15. 21 or more purples out of 100, that probability is 0.15. So again, we're in a bit of an awkward situation where the probability is not low enough to think it's impossible. I mean, if we repeated this whole experiment over and over and over again, 15% of the time, if the die is fair, we would observe these results. and 15 out of 100 is not that small. In order to quantify whether that probability is small enough or not, we need the concept of statistical significance. So the idea here is that we're going to reject the null hypothesis when the p-value is smaller than a certain value. We determine that the probability is small, so then we reject the null hypothesis. Often that threshold is equal to 0.05. It turns out that if we follow this whole framework and we reject the null hypothesis when the p-value is more or equal to alpha, then that guarantees that the probability of a false positive is more or equal to alpha. What is a false positive? False positive is if the null hypothesis holds, but we reject it. If it is true that this is a fair die, but we say that it is not. This will happen with probability less than or equal to alpha. If alpha is 5%, it will happen less than 5% of the time if we apply this framework. Proving this is not completely obvious, and we will do it in a separate video. So in this case, if we set our threshold to 0.05, and we need to obviously set this threshold beforehand, before looking at the value of the test statistic, our our results, our p-value that we observe is above. Okay. So in this case, we do not reject the null hypothesis because the p-value is not below this threshold of 0.05. Does that mean that we think the die is fair? So think about it for a moment. What do you think? Where would you put your money if I bet with you whether the die is fair or not? It doesn't necessarily mean that, right? It means that we don't have enough evidence against the die against the die being fair. In fact, I personally think that the die is not fair, and if you look at it has this pocket here to put some cards inside, so this side is actually different to the rest, which gives, more evidence to my hypothesis that the die is actually not fair. This shows you the limitations of the hypothesis testing framework. It's a very strict framework so that when we reject the null hypothesis, we're pretty sure that something interesting is going on. But if something interesting is going on, but the evidence is not overwhelming, as in our case, where, we rolled this guy 100 times and we saw something that we would only see 15% of the time if the die was fair, we consider that that's not enough. We need really stronger evidence against it. So you can see that in this case, in this sense, the null hypothesis framework is asymmetric. We just want to make sure that if we find something, it is really there. And that's it. What have we learned? We have learned these key concepts in hypothesis testing, the null hypothesis, which is this devil's advocate hypothesis that nothing interesting is going on, the test statistic, which is a function of the data that enables us to gather evidence against this null hypothesis, and the p-value, which quantifies to what extent the data that we're observing are consistent or not with the null hypothesis. And that's all I got. Thank you very much.